Nice. All right. We are live. Yes, we are live. All right. Welcome, everyone, to another stream. Today, we're going to try to get as much information as we can out of data centers. So, yesterday, I spent some time watching through one of the Stanford classes taught by David or Chase Lockmiller, who's the current CEO of Crusoe Energy. Oh, shoot. Okay. Take my internet shitting out. Oh, God. Okay, got some water. Okay, I think this is going to be a tough stream. My internet isn't doing too well, but I'll make it work while we have it. So, we had this video that we were watching yesterday, and it seems like Chase was basically saying these AI factories today, they're composed of 5 different components: your data, algorithms, compute, energy, and data centers. Crusoe is a company that really focuses on these two, so the energy and the data centers part. But really, all of these businesses are making money. I don't know if I'm saying this right, Cog Douglas, but this is the basic fundamental equation for GDP growth. It's the change in labor, the change in capital, and the change in technology. You take the sum of all three, and that is going to be equal to your GDP growth. So, in Chase's view, and this is really the broader view of Silicon Valley right now, AI is going to impact labor, and AI is going to impact technology. And it's going to grow at an unprecedented rate because usually new software tools, new hardware tools affects technology, but now it's really starting to bleed into the labor force as well. And so he has this 2 types of layers or stacks that he likes to bifurcate a data center into. There's the digital infrastructure and then the cloud, the Crusoe cloud area. So this is all of the computes, the data, the algorithms, they live here. And all of the data center, this is the steel, the energy, the grid, and all of the networking and electrical equipment that actually goes into the data center. Okay, so this is an interesting thing. At its most basic level, a data center is really just a building and cooling at its core. Maybe that's an oversimplification, but it becomes more complicated as you scale up. And there's chemistry involved, physics, engineering, all of this in one roof. So it can get pretty complicated. And what he is trying to solve, and what a lot of these hyperscalers are contracting Chase to really solve, is creating a shell that's powered so that you can easily plug in 500 to 1 gigawatts of compute. And it does feel like energy in the form of watts is really one of the core bottlenecks of this entire ecosystem. And so this is what their founding insight was. It was energy that was the bottleneck. And right now, there's certain hubs within the US where data centers are primarily located, Santa Clara being one of them on the West Coast. on the East Coast, Virginia, specifically Northern Virginia, next to Loudoun County. So this is a 2.1 gigawatt AI factory campus. So gigawatts, to put into perspective, what Chase was saying, it's about the same amount of power consumption, or really the power capacity that is used to provide energy to the city of Denver. So a city of about 300,000 people, I believe. How many people live in Denver? Okay, I was very wrong. 700,000 people. So there's first 8 buildings. This is for Project Stargate. This is in Abilene, Texas. And then this is kind of where it starts to get pretty interesting in terms of what is the actual economics of a data center, right? So there are certain areas here which I still don't fully have a 100% technical understanding of, but power distribution centers and transformers, these are kind of the gateway from an energy source, this gas power plant, or the broader electrical grid. And there's 3 separate types of power or energy setups. This gas power plant is what they call behind the meter. And the meter really is just the intersection between your energy source, be it a power plant, be it a wind farm, solar panel. It's the interconnection between these power plants and the broader electrical grid. So behind the meter, you're just actually co-locating this power plant right next to your data center, and you're not connected to the grid at all. You're just using this as the sole purpose is to provide energy to the data center. But these power plants at any time creates a lot more energy and power. I guess 2 things, right? So energy is measured in joules. Power is measured in watts. Voltage, I believe, is a form of electrical energy. I could be wrong. I think I'm going to have to get some clarification there. But energy is a unit of work. Power is work done per second, usually, or per unit of time. And so this needs to be distributed, first of all, to all of the different data centers within this campus. And then transformers, they play an important role in regulating the voltage that is supplied to each data center. Because at the end of the day, you have to have either a ceiling or a floor of how much power you can supply to, let's say, a rack of GPUs or CPUs. And so this is a pretty challenging technical problem from an electrical engineering standpoint. You also have chillers, so temperature and thermal regulation is also a very difficult challenge within data centers themselves. And typically, a lot of these things are liquid cooled, so liquid cooling is a big one. I believe any type of liquid is a lot I guess better could be the right term here at retaining heat or retaining coolness. You also have an uninterruptible power supply. So these are your batteries, the cooling distribution units, which I guess is going to distribute the cold water across the different types of GPUs, and then you have some diesel generators. So labor is a big bottleneck. Okay, so this is pretty interesting. He kind of has this expense breakdown, right? This is essentially building the shell of the actual data center. The bottom half of the stack. This right here, the digital infrastructure. Thank you. So the biggest costs here are actually the labor. So labor force is going to be the biggest cost. So that's construction workers, electrical engineers, mechanical engineers, plumbing or plumbers, networking people. So you have a broad, very large, diverse set of people. And then number 2 is materials. So things like steel, concrete, things to build the actual campus itself. Okay. The gas plant itself is about 3 million megawatts per megawatt. So if you have a 1 gigawatt power plant, it's going to be $3 billion to build right there. And 4.7 billion of labor. So this is the across the meter wind farm. Meter is the interconnection point with the grid. And this is kind of the meat of all of the spend. Half of it is going towards compute, GPUs, 4 billion per megawatt, or 4 million per megawatt is going towards networking. Yeah, so the total spend here is 60 billion, and you can see here, this is kind of the math behind what is the return on the possible investment. So annual revenue with managed AI services, he thinks that they can get to about 30 million per megawatt. And so you have a payback period of about 2 years. And really the crux of this problem is right now there's a whole debate going on between what the depreciation schedule is for a lot of these capitalized expenses. Like literally everything we just talked about are all capitalized on the balance sheet. It's not flowing through as OPEX on the income statement. So with that being said, the income statement, the P&L, could be either inflated or deflated based on what the useful life is on some of these GPU clusters, which, as we saw, is the primary half of all of the spend that's going into these data centers. Chase thinks it's about 6 years, ideally longer, if the hardware can be used for less intensive workloads, or if they get just retired completely. Because it's such a new technology, it's not 100% certain. I guess one thing that would be interesting to track is you had a lot of data center build out for these crypto farms back in 2021 and 2022. Are these GPUs still being used today? Like, let's say the NVIDIA A100s. And if so, how much value do they bring? So that's actually could be interesting to kind of look into right now, actually. Are the GPUs that were being deployed for the large crypto largely depreciated down to 0 as of 2026. What was the cutting edge back then? A100s? Oh, fuck. Deployed. Yeah, wrong word. Not delayed. Okay, so they didn't even use an AMD say Radeon RX 6000. Okay. A100s appreciated to 0 today. Yeah, okay, so this is an interesting call out from Gemini, if this is true, in the sense that these older chip generations are still being used for inference right now. And this is, I guess, the beauty of NVIDIA's CUDA software. Yeah, it's backwards compatible, right? When was this? March 5th. Okay, this guy, dude, he is a great salesperson, Jensen Huang. Okay, so this is actually a pretty interesting addition to this debate. So the depreciation of chips, right? still running full utilization, 6 years. Company shipped them. Hence the useful life 2020 to 2021. So this is being used for inference tasks. I guess that naturally begs the question, right? At some point, once supply catches up with demand for the compute chips, then will these later historical products depreciate at a faster rate due to less utilization? Most likely, so I honestly think the better question is when this will happen. Okay, and this is the beauty of backwards compatibility with CUDA, right? I'll give a little smiley face. Okay, so with that being said, I kind of want to switch gears here before I get in too deep. And today I want to spend some time looking at this. Bessemer Ventures released a roadmap of the AI data center stack, and I think this is actually very on topic of what Chase was talking about in his lecture. So this was released just this week, May 19th, 2026. It's currently May 24th. And they're kind of talking about the same things here. 6 opportunities in the AI data center stack: permitting, site selection, power generation, transmission, power conversion, middle mile of power, not to be confused with middle Earth orbit or medium Earth orbit, which I did yesterday, software and orchestration, construction, maintenance, and labor, and cooling technologies. So you can see here, none of this relates to the actual compute networking side of things. This is just all building that $20 billion shell per gigawatt that Chase was talking about in his presentation. Okay, so early 2026, 190 gigawatts of hyperscale data center capacity has been announced. I did not know that. That is crazy. What is sightline climate? Okay. This is actually a great chart. So if this is all of the operational gigawatts, I'm assuming. So 2026, more than half has just been announced. So where's the power bottleneck? Okay, so this I think is definitely worth snipping. Also, of the 31 gigawatts of capacity, yeah, slated for 2026 is still the announced phase. To come. And it said it takes about like 12 to 18 months. It's 12 to 18 months. Build out a data center and corresponding energy capacity to support it. So there's 190 gigawatts across 777 large data centers and AI factories announced since 2024. At least 16 gigawatts of capacity is slated to come online in 2026. Oh. Power purchase agreement. Accelerate deployment. Okay. And I know a Next Era ended up buying a company, right? Dominion merger. So this is a day before Bessemer released their report. Okay, I'll definitely come back and take a look at this, but let's not get distracted here. So 148 gigawatts planned, 21 gigawatts in construction, 12 gigawatts already operational. Global data electricity consumption is projected to more than double by 2030. Let's see if we can copy this image, paste it over here. So renewables is going to be the highest growth. Nuclear. On an absolute basis, and this is measured in terawatt hours, electricity generation for data centers to double to more than 1,000 terawatt hours by 2030. Okay. Every country innovating with AI. Data centers can be constructed within 12 to 18 months. What can I think? Okay, so that's interesting. takes 5 to 7 years for the data center to connect with the grid. Why does it take so long? Okay, I see. A lot of this, I mean, it sounds like more than half of this time is literally just regulatory bureaucracy. Okay, so it's starting to make a little bit more sense now, right? It sounds like the problem here is you're basically building a city in 2 years, like a full-on city with 700,000 people, a Denver-sized city. You can't just, for the sake of other people living around, and also for the larger electrical grid as a whole, you can't just literally plug it in within 2 years, maybe a year to 2 years. It seems like justified. It's somewhat justified. The rate and the speed at which these things are being stood up is just insane. It's insanely quick, and the electrical grid just isn't able to support that. And this actually has real impact on people's lives and could really negatively impact them if that were the case. So I think that from that perspective, it is as if can't talk. I consumed a copious amount of caffeine, so I am saying a lot of things. Maybe some of it isn't making any sense. But there is kind of, I can see that viewpoint, right? So the way to sidestep that essentially is to just build your own power supplies. And it seems like that's what a lot of these hyperscale and neo-cloud type companies are doing. And if they're lucky, they can find locations that are just very power efficient. There's already a lot of power infrastructure nearby that they can kind of just plug into, whether it's energy through wind, through solar, geothermal, nuclear, whatever it may be. Okay. I guess from this viewpoint, the regulation kind of did its job here to protect the interest of everyday people. I will say though, from the point of hindering innovation, it does seem like it's doing that. But I do think this is a worthy cost. And there is a solution here. It is to kind of build these behind the meter solutions. So it forces these hyperscalers to kind of get creative here. And yeah, that's an interesting idea. Wait, really? This is the same. Okay. Takes me to the same link. So that's behind the meter. All right. So this is a Bessemer stack. So it would be cool to kind of take a look at all of these different companies, spend some time researching, digging in. Yeah, the permitting problem definitely does seem to be pretty big, right? $5 billion is spent annually on complex infrastructure permitting. Don't know how much of this is actually focused on data centers. Guess be worth a read. Permit prep and execution service. Paces. Okay. 24/7 dispatchable solar power systems. I know this is actually founded by Jack Abraham. Yeah, all of a sudden I'm blanking on his VC firm name. Atomic. Yeah, Atomics. Atomic Ventures. Low levelized cost of energy. Beyond generation itself, the most durable businesses will own the hardware relationship with the data center operator and layer dispatch, optimization, or predictive controls on top. The power stack converges towards NVIDIA's 800V direct current architecture. We believe these types of companies also benefit from being embedded. Okay. So this would be cool to kind of see. So we have power generation. It's permitting license. Selection. Right. Yeah, there was power generation. So third is transmission, conversion, and middle mile of power, software plus. McGurney. I just randomly thought of the Visa CEO, Rory McGurney. I have to double check. Switchgear lead times now stretch beyond 60 weeks. High voltage cable and breaker backlogs are widely reported as the next constraint. Rack density, I guess, is becoming more dense. Yes. Wow. Alternating current to direct current and adds additional hardware. Yeah, so I would just be very interested to see. It does feel like climate as a whole has had a pretty tough startup and VC investment. In the past 2 years, ever since Trump became president, it is a very political area of investing. But I mean, it does seem like the problems here are pretty distinct, right? Okay, interesting. By directly using silicon carbide semiconductors to convert medium voltage alternating current directly to 800 voltage direct current. So solid state transformers collapse multiple discrete stages of legacy power conversion hardware into a singular. Huron Power is building Huron Link, modular medium voltage solid state transformer purpose built for 800V direct current power. I don't know what VDC, virtual data center. That'll be interesting. Like, how fast can you actually design and build one of these things? It's kind of like, can you do things faster over others? This is just a classic example of that. Flexible demand. So this is another big one that Chase was talking about as well. Construction, maintenance, and labor makes the entire build possible, experiencing massive labor shortages. Robotics, automation, AI-powered software are filling the gaps across 3 distinct phases of initial construction, ongoing operations. The most defensible players will combine automation with proprietary visibility, which includes predicting failures before they cascade, surfacing build quality. Yeah, okay, so the most attractive businesses in the cycle will merge. Size growth during this capex boom merge as on the other side as baked in operational infrastructure, durable, long duration economics, even if and after new builds. Yeah, I guess just looking at this transmission, power conversion, software orchestration, construction, and power generation are kind of the big sectors here. Let's see if we can Gemini. Excuse me. Let's see if we can Geminize this. You are my VC partner / analyst. This in this market map, help me analyze the permitting and site man, I don't have a draft chat. Okay. You are my VC analyst. Partner. Help me analyze sites. From this area. This market map. Startups are GeoForge, NY, Ixiom, Lorica, Scout, Permit Pal, Paces, Spark. Esri ArcGIS. Yeah, there's to the same analysis for transmission and power conversion. So municipal public grids, circumventing. Okay. Combinator. Engineered for. Okay, so it's been about an hour now. I think I'm probably gonna have to go soon. So thanks for watching this time. I think this will be definitely worth going into this map at some point later today if I have the time, which I'll try to make the time for. Okay, thanks for watching. Catch you guys in the next one.